So, in our last class we started capacitor and we saw how to find out the capacitance for parallel plate system, spherical system, cylindrical system, right. So, today in this session we will talk about how to find out distribution on the capacitor once charge is given, and we will also see how to make a single capacitor when there are so many capacitor connected. So, we will see series combination, we will also see parallel combination. So, let us start. So, before getting into series and parallel combination, let us see one simple example. So, you can read it. Two very large thin conducting plates having same cross sectional area are placed as shown in figure. They are carrying charges q and 3q respectively. So, this plate carries q charge which is from x is equal to 0 at distance d, and another plate which is at distance 3d carries 3q charge, right. Now, question is the variation of the electric field as a function of x for x is equal to 0 to minus 3 will be best represented by, as there is less space in the slide, I have used another slide. So, there are 4 variation given and you have to mark which one is correct, right. So, let us see, we know the procedure. First we need to distribute the charge. So, if I draw these two plates separately, say this carries q charge and this carries 3q charge, and we know the charge appearing this side. Charge appearing this side is q1 plus q2 by 2, that we have seen in conductor. So, if you have any doubt you can see those classes, right. Now, charge appearing on this side will be q1 plus q2 by 2. So, you have to add these two and divide by 2. So, 4 by 2 will give you 2q. So, this side charge will be 2q positive, right. As total charge is conserved, the charge appearing on inner surface will be like this is 2q. So, obviously this side minus q will come, or else you can apply formula q1 minus q2 by 2. So, q1 minus q2 by 2, I can see minus q here. So, this will be carrying minus q charge. So, this side it will be minus q, this side plus q, this will be minus q, right. Facing surface, as we know, carries equal amount of positive charge. So, charge appearing on this side of surface will be plus q. So, if this side it is plus q, total charge is conserved, like this total has to be 3q. So, charge appearing on other side of the surface will be remaining charge 2q. So, this is the way charge will be distributed once given to the plates, and using this I can draw electric field pattern, and I can also talk about the magnitude of the field in the different region. As I told you in conductor, that field here depends only on these two charges, and the effect of outer surface charges will get cancelled at this particular point. So, this 2q will produce field in this direction and this 2q will produce field in this direction, and they will cancel. But look at this minus q and this plus q will produce field in this direction, and this minus q negative charge towards the distribution, right. Positive charge away from distribution, negative charge towards the distribution, they will get added up. So, here if I want to write magnitude of field, this will produce q upon 2 epsilon naught, and this will produce q upon 2 epsilon naught. So, the field here will be q upon a epsilon naught in this region, right. Similarly, field here, now this negative charge will produce field towards and this positive charge will produce field away. So, the inner surface charge effect will get cancelled out at point outside the arrangement. But look at this one, this outer surface charge 2q will produce field in this direction, that is 2q upon 2 epsilon naught, and this will also produce field 2q upon 2 epsilon naught. So it will be 4q upon 2 epsilon naught, that will make it 2q upon a epsilon naught. So here field will be 2q upon a epsilon naught, right. Direction this way, and whatever happening this side, same will happen this side, right. So the magnitude of field here will be 2q divided by a epsilon naught, right. Now let us draw the pattern, then it will be more clear. So as we have negative charge this side and positive charge this side, line starts from positive charge and terminate at negative charge, field lines in this region will be like this. Look at this side, the field lines will be starting from positive charge and terminate to negative charge, and in this case it will go till infinity this way. This side charge and this side charge, they will produce field in this direction away from distribution, and the direction of field in this region will be something like this. So this is the way field lines will be there in a space. So between the plates this way, outside the place this side it will be this way, and this side it will be this way, right. You can see the magnitude outside is more as compared to the magnitude inside. Here we are getting 2a upon 2q upon a epsilon naught. So density of field line here will be more as compared to what we are drawing inside. So here field line density will be more. So it will be something like this. Now if I consider this direction, positive x direction for positive electric field, right, and opposite to that negative. So this will be in negative direction, this region it will be negative in direction, this region it will be along positive x direction, right, and this we have to figure out in the given variation. Like look at all these variation. This variation says throughout the region field will remain positive, right, this positive, 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 this is wrong. Similarly here it says it remains positive, this is also wrong. Now look at this one, this says that less than d it is negative, but greater than d in both the region it is positive. If you look at the diagram we have just discussed, that in this region also it is in negative direction, right. So here from x is equal to d to x is equal to 3d it is in negative direction, and x is less than d it is in negative direction. So this is also wrong because of this part. Now let us see last one. So 0 to d it is more than as compared to d to 2d. Let us see it again. So here magnitude of field or field intensity is less, that is q upon a epsilon naught, but in this region it is more, that is 2q upon a epsilon naught in magnitude, direction reverse, right, and whatever magnitude we are getting this side, same we are getting this side, right, 2q upon a epsilon naught. So here in this region from d to 2d it is less in magnitude as compared to it is between 0 to d, and then as you cross 2d again it becomes positive. When you cross 2d, this x is equal to 3d, x is equal to 3d, then it is positive, right. So from you can see d to 3d it is negative, and from there on it will be positive, right. So, this is the best graph, best suited graph, right. Now, let us see combination. So, when we have multiple capacitors, they may be basically connected in two ways. See, either it might be a series combination or parallel combination. It might also be possible that the connection might not be series or parallel. What to do in those situations we will see later, but for time being, if connection is simple, then how to reduce the circuit, right. So, two capacitors are connected and how to reduce the circuit, that means I want to replace this whole branch by a single capacitor which will give me the same effect. So, once connected with the battery, same battery, I will get same effect. And what is the effect in this situation? If this is V volt battery and say V volt battery gives Q charge to this arrangement, then I want to replace these two capacitors by a single capacitor which when connected with V volt battery extract Q charge from the battery. So, what should be the capacitance of this single capacitor, that we need to find out, and that we call equivalent capacitance. So, C equivalent. So, if these two, say this is C1, this is having capacitance C1 and this is having capacitance C2, I want to find out equivalent capacitance which can replace this arrangement, right. So, how to find out? As you can see in the circuit, that whatever be the voltage here, that will get divided into two parts. So, say V1 is appearing over first capacitor and V2 is appearing over second capacitor. V1 is appearing over first capacitor and V2 is appearing over second capacitor. So, what I can write? I can write V is equal to, here I can write V is equal to V1 plus V2. In the circuit, if you look at the supply voltage will be equal to voltage across sum of voltage across the branch. So, out of V, V1 came here and V2 appear here, we are writing V is equal to V1 plus V2, and we know that for capacitor if it carries Q charge, because charge is given by battery Q. So, if charge is given Q, whatever battery delivers, once switch is closed, it receives the same amount of charge, because the net charge on the battery is always 0. So, whatever it delivers, it receives back. So, it receives the Q charge. So, that means this way the charge must flow out through that plate, and if this is the way charge is flowing out, here it has to be like this. So, if I distribute the charge, plus Q is given to this plate and Q is taken from this plate which was not earlier having any charge. So, charge appearing on this one will become minus Q. As Q goes out, this will have plus Q charge. Similarly, as charge goes out to this one, it receives Q charge, it will be plus Q, and here charge flows out. So, this will be minus Q, right. And as we know that if this is carrying plus Q charge and minus Q charge, Q1 plus Q2 by 2, 0, Q1 minus Q2 by 2, this will come Q, right. Q1 plus Q2 by 2, 0. That means there is no charge appearing here, whole charge will completely appear on the inner surface of the plate, right, and this will be minus Q. Similarly, same thing happens here, plus Q appears here and minus Q appears here. So, this is the way charge will be distributed once switch is closed. So, as soon as you close the switch, immediately charge Q will be given by the battery, and battery makes sure that it receives same amount of charge. So, whatever it gives it receives back, and this goes into the system, and this is the way charge will be finally distributed, right. Now, voltage drop across this capacitor, Q is equal to CV, Q is equal to CV. So, for first capacitor, capacitance is C1. So, voltage drop V1 is Q by C1. So, here I can write Q by C1 plus. For second one, similarly I can write, both are carrying same charge because they are connected in series. There is no division of charge at the junction. There is no other branch here which can take some part of the charge out. So, whatever is getting into this one, same is getting into this one, they have the same charge. Here I can write voltage Q by C2, right. Now comes this one. So, if it receives the Q charge and here Q charge will be taken back, then obviously this will be carrying plus Q charge, plus Q, and this will be carrying minus Q charge, right, and its capacitance we are assuming C equivalent. So, what we require that once connected to V volt battery, it extract the same charge as drawn by this whole branch. So, now from this circuit I can write Q is equal to CV. So, Q is equal to CV here, Q is equal to CV, C equivalent V. So, from here I can write Q is equal to C equivalent V, that means V is equal to Q by C equivalent. So, here I can place the value Q by C equivalent. As you can see that Q gets cancelled out, and what we are getting, that 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2. So, this is when capacitors connected in series. I can combine these capacitor and make a single capacitor producing the same effect as produced by this whole combination or this branch, right. I may have one more capacitor connected, C1, C2, C3, C4. So, same way I write 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus 1 upon C4, so on, right. So, this I have derived only for 2 capacitor, but this is valid for a number of capacitor. Only thing, 1 upon C1 plus 1 upon C2 plus 1 upon C3, you have to keep adding, right. So, I hope series combination is clear, right. Now, let us move to parallel combination. So, in this case, as you can see that second terminal of first capacitor, this is second terminal of first capacitor and this is first terminal of first capacitor, right. Similarly, this one is first terminal of second capacitor, and this is second terminal of second capacitor, right. So, when second terminal of first capacitor is connected to first terminal of second capacitor and there is nothing connected in between, if I connect any capacitor here, then they are no longer in series combination, right, because here charge is getting divided, right. So, if second terminal of first capacitor is connected to first terminal of second capacitor and first terminal of first capacitor and second terminal of second capacitor are connected to some other device, then the combination is called series combination. That means at junction there should not be any division of charge. So, there should not be any device connected at junction, then only these two will fall in the category of series combination, right. So, here there should not be anything connected, then only it will be series combination. I hope this point is clear. What we call series combination, Once charge is flowing from this capacitor to this capacitor, there should not be any division. If there is any division here, these two won't be in series combination, you cannot apply this formula. So make sure that nothing is connected between these two capacitors, right. Now let us take parallel combination. So as you can see in this situation, first terminal of first capacitor, and first terminal of second capacitor, they are connected together, and second terminal of first capacitor and second terminal of second capacitor, they are also connected together. So you take first capacitor, you take second capacitor, to take two terminals and just join them, then combination is said to be parallel combination. So this is parallel combination, right. So as soon as I close switch, this battery delivers some charge Q, and immediately it will make sure that it receives Q from or Q at other end. So once this charge reaches here, there are two paths available for charge to flow. One is this one and another is this one. So this charge gets divided into two parts. Let this be Q1 and this is Q2. So this Q2 will flow and reach here, Q2. Let the capacitance of this capacitor is C1 and this one is C2, right. So once Q1 reaches here, it receives Q1, and immediately here, to have this Q, this will deliver back Q1 and this will deliver back Q2, and they will get combined at the junction, and finally this is a complete circuit. So you have to first complete the circuit, making sure that battery receives the amount of charge it has given, right. So whatever flows into this one through this branch, same thing must come through this branch, and they will get combined, and then Q flows back to the battery. Now again the same logic, like it receives Q1 and it gives Q1. So here this will be minus Q1 and here this will be plus Q1, and if this is the way charge is given to the plates, this side does not carry any charge, whole charge appears here. So this plus Q1 will appear on the inner surface, and right in front of that minus Q1 will come, okay. And same logic I can extend for this situation, like if it receives Q1 and it gives Q2 and it gives Q2, then here it will be plus Q2 and this will be minus Q2. Now we have completed the distribution. Let us analyze the situation. Again, what we want? We want to replace the whole arrangement by single capacitor which gives me the same effect as given by these two capacitors in combination. So I am in search of a capacitance which gives me same effect as given by these two in combination. Effect means this capacitor draws same charge Q as drawn by these two in combination. So Q charge will be given to the arrangement and it will be received back by the negative terminal of the battery. Right. So plus Q and minus Q. And I am calling this as C equivalent, right. So these two I want to replace by a single capacitor having capacitance C equivalent. Now, so previous case if you look at, here voltage was getting divided, this was having potential V and one part of that V came across this capacitor and the remaining part came across second capacitor. Once you connect these two in parallel combination, like this one and this one, these two are connected in parallel, then the potential across this capacitor and potential across this capacitor both will be same, and that same value is V only, right. So here potential is not getting divided, right. Here potential is not getting divided. What is getting divided in this situation is charge. So charge gets divided into two parts. While in the previous case, charge in both the capacitors was same because they were connected in series. There was no division of charge. So whatever flowing through this one, same flows through this one, right. So previous case, charge through both the capacitors same. They had different potential difference. While in this situation, as they are connected in parallel, whatever with the voltage drop across these two terminal of second capacitor and voltage drop across these two capacitor of first capacitor, they must be same, and that same value will be equal to the voltage of or potential difference of battery, right. So division is for charge. So I can write Q is equal to Q1 plus Q2, right. And if I just look at this capacitor, the voltage drop across these two terminals is Q is equal to CV. So for this capacitor I can write Q is equal to CV. That means Q2 is equal to CV. Similarly for this capacitor I can write Q1 is equal to CV. So these two values I can substitute in the equation. So let us substitute the value. So C1V plus C2V, and left hand side of the equation, this value I can substitute from this circuit. Here Q is equal to CV, Q is equal to C equivalent V. So I can substitute the value of Q, that is C equivalent V. As you can see, V will get cancelled out. We are getting C equivalent is equal to C1 plus C2. So when you are connecting capacitors in parallel, their capacitance will get simply added. So add the capacitance of these two, you will get the equivalent capacitance, right. So I have taken example for two capacitor. We may have 3 or 4 capacitor, n number of capacitor. We have to just write C1 plus C2 plus C3 plus C4 so on to get the equivalent capacitance of the arrangement. So series formula is 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2, and for parallel we have formula C equivalent is equal to C1 plus C2, right. So procedure is clear. Now from here onwards, instead of following this procedure, we will directly apply the formula C1 plus C2 for parallel combination, and 1 upon C1 plus 1 upon C2 is equal to 1 upon C1 1 upon C equivalent for series combination, right. So let us see some examples. Okay. So circuit might be given in such a way so that initially you are unable to observe which is in series combination and which all are in parallel combination. So the logic is like series combination between or at the junction of joining of two capacitor, there should not be any other capacitor or any other element connected. This is the concept for series. For parallel, first terminal of first capacitor and first terminal of second capacitor, they are connected together, and second terminal of first capacitor and second terminal of second capacitor, they must be connected together. If you use this logic here, you can easily figure out what all are in series combination and what all are in parallel combination. See, as I can see that this and this, they are directly connected. Its first is connected to first of this one and second is connected to second of this one. These two are in parallel combination. So I can reduce this part of circuit first, right. So when you add these two, formula is C1 plus C2, so it will become 200 picofarad, right. Once you replace this by a single capacitor, that single equivalent capacitance and this capacitor both will be in series combination. You can have a look. This capacitor I am drawing it here, right. This combination I will draw here. So this whole thing I am drawing here, that is 200 picofarad, right, and this single one 200 picofarad, right. And then look at this bigger one, this is 100 picofarad. And then we have this 200 picofarad and this is 100 picofarad. So I first reduce this part of the circuit, I got this design. Now you can see these two are in series combination, right. This first one is connected to second one of upper and its second one is connected to some other elements. So these two are in series combination. Series combination formula 1 upon C1 plus 1 upon C2 is equal to 1 upon C equivalent. So 200 when you add by this formula you will get 100. So this whole thing can be replaced by a single capacitor of 100 picofarad. So I will put 100 picofarad over here. So 100 I am putting. As soon as I reduce that branch, I can see again these two are connected in parallel combination. So this 100 and this 100 will make it 200 series combination C1 plus C2. So this whole thing, look at this whole thing, you can see that these two are connected in parallel combination. So these two are connected in parallel combination, formula is C1 plus C2. So this arrangement equivalent capacitance will be 200 picofarad. So I will erase this part of the circuit and I place 200 picofarad, right. So 200 picofarad. Now you can see that circuit has become very simple as compared to this one. This has become very simple. Now these two are in series combination, 1 upon C1 plus 1 upon C2 is equal to C equivalent. So this whole thing will become 100 picofarad. So this whole thing I am talking about, this will become 100 picofarad, right. So I will remove this and put 100 picofarad over here. So this 100 and this 100 will make it 200 picofarad. So C equivalent across X and Y. So C equivalent capacitance across these two terminals is 200 picofarad. So step by step you see different parts and start reducing it. In the end ultimately you will get C equivalent. So I hope you understood the application of series and parallel combination. Let's take one more example, it will be more clear. So I have taken this example, right. So sometime what happens, in a particular branch a conducting wire is given to you, right. Conducting wire won't have potential difference across its two terminals. So that means whatever with the potential of this terminal, same will be the potential of this terminal, as these two are connected by conducting wire. So wherever we see conducting wire, we can assume that both the terminals are same, and first we try to simplify the circuit, and then using series parallel combination we reduce the circuit. So there are two steps involved. First one is try reducing the circuit or try simplifying the circuit. Once circuit is simplified, then you can easily see which all are in series and which all are in parallel, and you can reduce the whole arrangement. So let us start. So across A and say this B, across AB I want to find out capacitance, right. Now I can see one conducting wire over here and another conducting wire over here. As this one is directly connected to this one by conducting wire, I can name this terminal as A, because both have same potential, right. So I can just name this as A and this as A. Now look at this one, these two are connected by conducting wire. So if I name something here, for example A, B I have considered, let us consider C. So this as C terminal, this will also be C terminal. So basically I am seeing there are three major junctions, and I want to find out equivalent capacitance across AB, right. But I have to pass C to reach to B. If I start from A and I have to reach to B, then you can see that in this branch I have to cross C and then I can reach B. Through this branch also I have to cross C and then reach to B, but while in this case to reach to B I have to just cross this capacitor. So C is the intermediate terminal, and while simplifying you can draw C anywhere. If you do not select a proper point to place C, circuit may again become more complicated, and how to place the point C you will learn from the practice, right. Here this circuit is very simple, like no matter how you draw it, it does not make any difference, but once we will be talking about symmetry and all, there placing these intermediate terminal plays very important role. So how to select C and where to place it, that we will learn in circuit symmetry, but for time being this is a simple circuit, it will not make much difference wherever you select it. So this is A terminal and this one is B terminal, and there is some intermediate terminal C, right. So let us start placing all capacitors. So I can see, I will start from this branch. Between A and C there is one capacitor, between A and C there is one capacitor. So this over. Between C and B there is another capacitor. So between C and B I will place one capacitor. So this also over. So two capacitor over, and keep marking, because in exam what happens, generally we place the capacitor and then we forget what we have placed. So you may end up getting more number of capacitor or less number capacitor in the simplified diagram. Obviously the C equivalent what you are going to calculate or what you are going to get will be different to what actually it is. So once we complete a simplified circuit, we will count the number of capacitor in both the diagram and we will check whether both are coming same or not. So these two over, now these two. Again between A and C I can see this capacitor, between A and C I can see this capacitor, so this one over, and between C and B I can see, C and B I can see this capacitor, this one is over. right. Now between A and C, here between A and C I can see one more capacitor. So I will place one more capacitor between A and C, and then the last one A and B directly connected by this capacitor. So this one also over, this one also over, the last one is between A and B. So between A and B, right, this way I can draw. Now we need to simplify. Here I can see 3C and here I can see 2C. These three are connected in parallel. So C1 plus C2 plus C3, 3C, 2 are connected in parallel, 2C, right. So after simplification we are getting this design, right. So we are getting this design. We can further simplify it. These two are connected in series combination. Formula is 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2. That can be written C1 C2 upon C1 plus C2, that is C equivalent. So for series combination I can apply the formula C1 C2 upon C1 plus C2. So once you do C1 C2 C1 C2 upon C1 plus C2, 3 into 2, this will give you 6, 6 divided by 3 plus 2 will give you 5. So here you will get 6 C by 5. So this whole thing using series formula is coming 6 C by 5, C1 C2, you can see C1 C2 upon C1 plus C2, right. So I can reduce this branch further. Six C divided by 5. So 2 capacitors I converted into 1 because they were in series. I apply this formula. Now I can see 2 capacitors again which are connected in parallel combination. So this I need to add with this one. So now formula is C1 plus C2. So C equivalent will come this plus this, that is 11 C by 5. So 11 C by 5. So this is the equivalent capacitance of this arrangement. So as compared to previous case, you can see here there was no conducting wire, every branch will have capacitor. I start simplifying it and I start getting series parallel combination. That way I reduced the whole circuit and finally I got equivalent capacitance. While in this problem you had 2 conducting wire, so directly we were unable to see what combination this with this one or what combination this with this one. So if you look at the circuit, now see this one is connected across AC and this one is connected across AC. So these two are in parallel combination. Similarly look at this one and look at the upper one, that is also connected between AC. So this and this, they are connected in parallel, right. So sometime we are unable to visualize directly, but once we simplify, it's easy to predict what all are in series combination and what all are in parallel combination, right. Now let's take one more example. So I'll add something in this situation so that you learn how the problem become more and more complicated. Now see this one. So there is a big plate big plate 5A cross 5A, right. So, I will try to draw this diagram in 3 dimension. So, there is big plate like this is 5A and this is 5A. Now, above this plate there is this arrangement. So, step by arrangement, so this is the way this side is there, right, and same as other side. Now, I hope this 3 dimensional diagram is giving you some clarity ki how the situation is. So, this is 5A, A, 5A, right. That means area of every part here, this part, this is A and back side it is A. So, this will be A square. So, this area will be A square, right. Similarly, look at this one. This is also A square. This one A square, again you will be getting A square here and A square here. So, now you can visualize the whole thing as we have a whole plate 5 by 5 and A square, A square, A square, A square, A square and then A square, A square. This way we will be having the arrangement. Now, the main thing is, if I ask what is the capacitance, as you can see that this A square and its projection over here, this and this and this one, they are forming one capacitor. This plate and this plate, this part, they are forming one capacitor. Then this one and the below one, this is also forming one capacitor, right. Then this plate and the below part, they are forming one capacitor. So, I can see altogether there are 5 capacitors of different capacitance, because the gap between them will be different. Here the gap is this gap, look at this gap. This gap, this is D, this is D, this is D, so this will be 3D. Now, look at this one, this is 2D, this one is D, this is again 2D and this one is 3D. So, I can see there are 5 capacitors C1, C1, C2, C3, C2, C1, whatever the capacitance here, same with the capacitance here. Okay. Let us write them separately. I hope you understood from this 3 dimensional diagram how the figure would be, right. Now, it is time to write the capacitance. One more thing, in what combination they all will be, because this is a conducting plate, and these joints are also conducting. So, these vertical plates, they are also conducting, that means they all will be at the same potential. So, these all will be at same potential, and this obviously this is a single plate, this whole thing will be at the same potential. So, all these 5 capacitors, they are in parallel combination. So, we need to add their capacitance to get equivalent capacitance. So, I will remove this part and we will write for so one by one I will write the capacitance. So, the situation is clear. So, equivalent capacitance for this one, epsilon naught A by D, right, epsilon naught A square by 3D. So, capacitance of this one I have written here. Now it's time to write the capacitance for this one. So again epsilon naught A by D, epsilon naught A by D plus, so these 3 over, now we are going to write for this one and this one, right. So epsilon naught A square divided by 2D plus epsilon naught A square divided by 3D. Now you can simplify and you will get C equivalent. So sometimes instead of connecting capacitors and battery by conducting wires like what we have just seen, these type of way circuit is given, but sometime this way circuit might be given, like plates will be there and you have to find the equivalent capacitance of the circuit, right. So let us take similar example so that this concept also gets clear. So here I have taken 4 plates and they are connected by these two. First and third they are connected by conducting wire and we are taking 2 terminals out, which A terminal is connected to second plate and B terminal is connected to fourth plate, right. So I just want to find out what is the total capacitance of this arrangement. If you look at the diagram, can by seeing you are able to tell which two are in series combination and which two are in parallel combination. Now from diagram it is difficult to say. So our first step to reduce or simplify the diagram and then we will be in the position to say which two are in series and which two are in parallel. So when such type of diagrams are given, our first step is simplifying the diagram, and process of simplification I already told you that as these two are connected by conducting wire, I can name it as intermediate junction, for example say C. As this and this, these two are connected by conducting wire, the potential here and potential here will be same and it can be named as a single terminal C. So from A to B through C, same as previous problem, right. So A, B and some intermediate terminal C. As look at the problem, each place has area, A area is given, separation is D, separation is also given and equivalent capacitance between A and B. So this gap is D, this gap is also D, this gap is also D, right. So if area is same, gap is same, they all will have same capacitance. I can see one capacitance here, over here, one capacitance over here and one capacitance over here. So I can see there are 3 capacitors, right. So that I need to connect here, as you can see between A and C, right. So instead of just naming the plate, best thing we can do, we can name the surface. If I name the surface this way, then we can keep track of every surface what we are getting after simplifying the diagram, because higher level problem charge on a particular surface will be asked. So if you just simplify the circuit, again you have to see which surface is where and it takes longer time. So just to reduce the time, start from naming the surfaces itself and then connecting it in or between the given terminals, right. So, this upper surface I assumed A, below one B, this is C, this one is D, and then E, F, G, H. Now, as you can see, A, this upper one is C, which is facing B, and that is connected to C. This whole plate is connected to C, right. So, if I draw two surfaces, what I am saying is, do not get confused, here terminal name is also ABC and face name is also ABCD. If you have any doubt, you can assume XYZ also, right. So, better do one thing, I will assume this to be capital A instead of A, and B I will assume this to be capital A, this to be capital B, and this is capital C. Now, there is no confusion, surface name we are writing with small a b c d and terminal name we are writing capital A B C D, right. Now, so terminal name capital A B C D. A, B, C. Now, look at what I was telling, the plate which is connected to A, its top surface which is C is facing B. A plate's C surface, this is C surface, is facing B surface of plate which is connected to C, right. As there is nothing on this side and there is nothing on this side, this surface will not be the part of any capacitor. So, you need not to worry about this A and this H. Again, there is no plate or there is no plate above this and there is no plate below this. So, this H and this A will not be the part of any capacitor. If it is not a part of any capacitor, we need not to worry about these two, right. So, we are worried about what all facing surfaces we have. So, I am worried about these two, I am worried about these two, and I will see these two, right. So, I will not draw A and H because they are not part of any capacitor, right. Now, look at this one, A is facing C, A is facing C, we have one more capacitor over here, the one which is connected to A, this side surface is D, this surface is D and it is facing E. So, this will be E. So, this gap is also over, this gap is also behaving as one of the capacitor, and now look at this one, C and between C and B, look at this region, C is connected to F, C is connected to F, and that F is facing G, right, F is facing G. Now, you can see that this is behaving as one capacitor, this is behaving as one capacitor, this is behaving as one capacitor. There are three capacitors I can see, out of that two are parallel. So, as these two are parallel, I can write C1 plus C2, as the gap between them is same, area is also same, every space here, every space is behaving as capacitor of capacitance epsilon naught A by D, right. So, epsilon naught A by D, epsilon naught A by D, epsilon naught A by D. Let us for time being write that as C. So, this is C, this capacitance is C capacitance, C capacitance, C capacitance. So, these two are in parallel, add these two you will get 2C over here and then C here, and these two are connected in series, C1 C2 upon C1 plus C2. So, C equivalent will be 2C into C divided by 2C plus C, that we are getting 2C by 3, 2C by 3, where C is, because you have to give answer in terms of area and the separation, C is, so this can be further simplified as epsilon naught A by 3D. So, this is the capacitance of the given arrangement, and these are the steps you need to follow. So, conducting wire, same terminal, circuit was not that simple, we cannot directly predict series parallel combination, we try to simplify the circuit, one circuit got simplified, we got series parallel as well as parallel combination, using the formula we got the final expression. And was the use of naming the surfaces, next example I will tell, right. But for time being, how to find out C equivalent or equivalent capacitance, this is clear in this case as well as previous case where there were plates only, right. Let us take one more example based on same thing this way. So, topmost and the bottommost, they are connected by conducting wire and you are asked to find out the equivalent capacitance, right. Again you can see as these two are connected by conducting wire, I can name them as a single terminal C, right. And then comes naming surfaces. So, small a, b, upper surface, lower surface, facing is C, then lower is D, E, F, G, H, right. And we are going to follow the same procedure. A, C and B, and now let us connect plates. A, upper surface C which is facing B, upper surface C is facing B which is connected to C, right. So, A is upper surface C which is facing surface B and that is connected to C. This is over. Is another surface D which is facing E and connected to B. Is another surface D facing surface E which is directly connected to B. So, this region behaving as capacitor, this region behaving as capacitor, right. Now, C and B, right. So, last one, B's, this lower surface F, B's lower surface F facing G which is connected to C, and as the gap between all the plate is same, here it is say D, this gap is D, this gap is D, and I am assuming C is equal to capacitance for any one of the spaces epsilon naught A by D. So, C. Now, it is very easy to decide which two are in series combination, which two are in parallel combination, and how to simplify the circuit. So, these two are in series combination, C1 C2 upon C1 plus C2. If this is capacitance is C and this capacitance is C, then upper one will get reduced to C by 2 parallel combination formula, and the lower one, which is C, now comes in parallel with C by 2. So, C equivalent, I can write C into C by 2 divided by C plus C by 2. So, if you simplify, here I can see 3 and this 2 and 2 will get cancelled out. I can see C by 3 and that C is epsilon naught A by D. Into. So, all such type of problem can be simplified using the basic concept of conducting wire and simplification, right, will give you final answer. So, let us take one more example here. Let us make circuit little more complicated. So, I will create one more problem here and I will try making circuit, the same circuit, little more complicated. So, if I place one more plate and instead of asking potential difference across A, B, if I ask potential difference, let us take one terminal out. Okay. So, I added just one terminal and that is facing the plate which is connected to C, and I am calling this terminal as D, right. So, I just added one more plate in the previous question, so that we will be having clarity how to solve the problem completely, right. I can also connect this plate by conducting wire which is connected to A or connected to B, right. So, let us connect these two. Now, this is our circuit. There are two conducting wire connecting these two plates, right, and this is terminal A, and I am calling this terminal as D. So, let us do one thing, just add one more plate and we will call that terminal as D, because I just want to increase the number of terminals. Now, this is a complete diagram and I am assuming that everywhere gap is D only, right. So, here gap is D, though in diagram it looks little larger, but it is D only. So, this is our diagram and I want to find out equivalent capacitance across AD, CAD. So, across AD, C equivalent AD I want to find out, right. So, now B will become intermediate terminal. So, A B, C, and then final terminal is T, right? And name the remaining surfaces as something came below H. Now this space will also behave as capacitor. So A, B, C, D, E, F, G, H, I, J, K, L, and as nothing is below L, there is no role of this surface. Nothing is below, above A, there is no role of this surface. Now these surfaces gap will behave as a capacitor, right. So A and B, so I have drawn B here. So let us start with AB. A's D is facing B's E. A's D is facing the surface E which is connected to B. So this over, right. So as there are so many spaces, I have to mark each and every surface or every gap once I have drawn it here, right. Now B's F and C's G. B's F facing surface G of C. So this one is over. Now C and B, look at this space. C, H surface, C, H surface and B's I. They are connected. So this space is over. Now this one, D and B, D and B. So B is here, I will put one plate here. Now B is J is facing D's K, B J is facing D's K. Now this over, only one is left, that is between A and C. So between A and C, A and the facing one is C is facing B, C is facing B. So now I can reduce these two, this will become 2C. So I am directly drawing, this is C, 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 and this combination will give you 2C, right. And so I will place 2C over here. So I will remove the capacitor and I will place single capacitor 2C, because they were in parallel combination. So now I have placed 2C over here. Okay. Now I need to find out capacitance across AD. If I just simplify it, then this you can see in series combination, this you can see in series combination. So 2C and C will give you this, look at this part across these two terminals, this part you can see 2C by 3, C1 C2 upon C1 plus C2. So 2C by 3. So I will convert into single capacitor 2C by 3 and circuit will become further simplified. this become 2C by 3. Now I can see that these two are connected in parallel and then this is connected in series. These two are connected in parallel. So C plus 2C by 3 will give you 5C by 3. So this whole thing will become, this whole thing I am talking about, this will become 5C by 3, right. Five C by 3. This 5C by 3 and this C, they are connected in series. So across AD, capacitance will be C into 5C by 3 divided by C plus 5C by 3. Simplify this one, 3 will get cancelled out and you can see 8 over here, that means 5C by 8 I can see. So no matter how many wires are connected, how many plates are there, procedure is that only. Once you simplify the circuit, then it will get reduced in the form where you can easily solve, right. I hope this is clear. So I hope you enjoyed today's class. Thanks for watching.